New pictures caught by the James Webb Space Telescope have staggered specialists. As opposed to extending our view of the universe, these pictures uncovered an upsetting reality. Our continuous cognizance is deficient in getting a handle on the conceivable outcomes of the universe in its beginning phases, where the speculation of the Big Bang appears to reach its limits. This drives us to ponder new hypotheses about its origins. The inquiry emerges with respect to how the universe was molded in detail and why this new disclosure challenges even the most experienced analysts. To find out more about the Big Bang and the complex subtleties of the discovery, how about we inspect the idea of the Big Bang itself? In disdain of standard reasoning, the Big Bang was not a blast in previous space. Rather, it was space itself that began around 13.8 billion years ago, alongside matter and time. A peculiarity in material science and cosmology describes focuses where gravity is so intense that the arch of spacetime becomes limitless. Today, following billions of years since the start of the universe, we see that our huge home is part of a fantastic cycle. For specialists, this addresses a key part of the universe since its very existence. It's plainly a ceaseless development, but it's pivotal to grasp that the universe isn't floating into previous space. Maybe space itself is persistently extending in size. According to current hypotheses, the first stars began to shine somewhere in the scope of 200 to 300 million years after the Big Bang, marking the finish of the supposed Dark Ages. This was the point at which the first iridescent celestial objects coalesced to form mature systems. However, how rapidly these galaxies formed remains a confounding secret. An abundance of information arose through the first pictures captured by the James Webb Space Telescope in July 2022. Specialists revealed that the telescope had identified different galaxies, some of which had already existed around 300 million years after the development of the universe. However, as opposed to the endless structures formed much later, these early galaxies were altogether more modest and less huge. This aligns perfectly with the scientific model accepted by specialists. The density of matter in the early universe was simply not adequate to result in worlds the size of those observed today. What began as the identification of 6 shining redshifted spots from the James Webb Telescope ended up triggering quite possibly the most critical galactic crises in recent times. Although these newly found worlds are similar in age to recently recorded worlds, they are all around as large as our own Milky Way. This has created a captivating mystery. In Big Examination, subsequent to examining a series of pictures caught by the near-infrared camera, specialists identified the aforementioned light sources using redshift to confirm that the light from these objects took more than 1 billion years to reach our eyes on Earth. Thus, we are dealing with structures that had previously existed around 570 million years after the assumed Big Bang. By dissecting the attributes of these designs, it was concluded that the Webb telescope had captured 6 early worlds in the pictures. Surprisingly, these universes were so enormous that they challenged normal suppositions in cosmology. Rather than finding the average, more modest galaxies, structures were identified that were almost as extensive as our own Milky Way, regardless of having formed early in the universe's history. Assuming we proceed to examine the data accumulated by the James Webb Telescope, this gravitationally bound bunch of stars was already more than 10 billion times the mass of the Sun at that time, with one possibly outperforming the 10 billion solar mass mark. However, whether this scenario is accepted, the mystery remains unsettled. Indeed, even for this case, there would be significantly more luminous mass in the early universe than previously anticipated, presenting a problem. The identified objects contradict practically all conventional cosmological hypotheses. Whether only one of these galaxies ends up being real, it would challenge our earlier assumptions. Besides, the density of matter in the early universe would have to be a few times more prominent than beforehand expected to account for this peculiarity. Another likewise bizarre explanation relies on how these galaxies formed in a way that remains completely dark to us. These revelations and the conversations surrounding the Big Bang have prompted numerous scientists to drift away from this hypothesis. Various astrophysicists with alternative perspectives feel their points of view are not being heard in scientific journals. Even those who express doubts about existing theories are often labeled as ridiculous motivations. Yet, obviously, even specialists who still advocate for the theory of how things came to be are continuously faced with questions without conclusive responses. These requests include specific issues like why and how, 13.8 billion years ago, something literally arose from nothing. Could something truly start from nothing? Or was there some triggering event? Or was it all just an accident? Steven Weinberg pointed out that the concept of time, as we understand it, began exclusively with the Big Bang. Thus, this process could not have been set off by something outside it. A similar contentious question relates to the consistency of radiation and density throughout the universe. Regardless of which direction or at what distance we look on a larger cosmic scale, we find similar densities and distributions of galaxies, nebulae, and radiation everywhere. Regular examiners explain this peculiarity through the theory of cosmic evolution. However, different specialists take this assumption further with a theory of tumultuous evolution. According to this thought, evolution has only stopped in specific regions, like bubbles, and continues endlessly elsewhere. This suggests that various universes could be forming in these bubbles, each with its own unique physical regulations. Within this model, a critical inquiry emerges. What if the universe doesn't represent the whole? More intriguingly, consider the possibility that another universe existed before our own. In this case, the Big Bang would become part of a larger cycle. According to this perspective, our universe is part of a more prominent, diverse design. Within this structure, the chance of an immortal pattern of breakdown and restoration of the universe is advanced. However, this is not the only perspective presented in the realm of cosmology. Besides the hypothesis of the universe's beginnings in 1955, for example, an article appeared in NASA Space Times contending that there could have never been a Big Bang, since the universe has existed for an infinite time. In this view, the expansion of the universe would be non-existent, and the consistent arrangement of matter could give the impression of a steady evolution. Additionally, another intriguing theory arises from the realm of quantum physics and string theory. Some tests have proposed that our universe and all that in it might simply be a flat, three-dimensional image projected onto a surface. Hence, there is a plausible idea that our reality is a result of a higher simulation. While this could seem like the plot of an unconventional sci-fi film, it might indeed be connected to the Kardashev scale, which gauges the level of progression of a civilization based on its capacity to harness energy. If there were a Type 3 civilization able to fully harness the power of an entire universe, it might have created a perfect simulation. Getting it right in such a circumstance is a very tangled matter. Investigating the depths of cosmology and the beginnings of our universe leads us into a domain of significant mystery and ongoing scientific inquiry. The new pictures caught by the James Webb Space Telescope have reignited conversations about the actual texture of our world, testing laid-out speculations and inciting researchers to reevaluate essential parts of cosmological understanding. At the core of this inquiry lies the hypothesis of how things came to be, an underpinning of current cosmology. As indicated by this hypothesis, around 13.8 billion years ago, the universe arose out of a phenomenally thick and hot state, growing quickly and resulting in space-time and matter as we grasp it today. This cosmic event is not just a blast inside prior space. Rather, it might include the very beginning of space itself. The concept of a peculiarity where gravitational forces are so extreme that space-time becomes boundless supports our understanding of this early-stage epoch. However, the discovery of early systems by the James Webb Telescope challenges our assumptions about how rapidly structures formed in the universe's earliest stages. These systems, identified within a few 100 million years of the Big Bang, appear astoundingly developed and massive in opposition to assumptions based on current cosmological models. One of the big inquiries raised by these findings is the concept of vast expansion. As indicated by the prevailing theory, expansion happened within parts of a second after the Big Bang, causing the universe to develop dramatically. This rapid development would make sense of the consistency of the cosmic microwave background radiation observed across the universe today. However, the new disclosures propose intricacies in the early universe's development that may require changes to inflationary models. The development of universes like those seen by the Webb telescope prompts cosmologists to reconsider the circumstances and cycles governing the universe's initial development. These galaxies, now critical in size and mass, suggest a density of matter that surpasses past estimates. The mystery extends while considering how such enormous designs could shape and develop in a relatively short cosmic time frame. Besides, the discovery of these early systems raises interesting inquiries about the nature of dark matter and dark energy, two elusive components that comprise the majority of the universe's mass and energy content. While dark matter is accepted to provide the gravitational platform fundamental for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In accordance with these astrophysical mysteries, theoretical physicists are investigating alternative cosmological models that challenge the regular Big Bang perspective. Some hypotheses suggest that our universe is simply one among many in a vast multiverse, each with its own unique physical regulations and constants. These thoughts, emerging from advancements in string theory and quantum cosmology, propose a more complicated and interconnected universe than previously envisioned. One thought building up forward movement is eternal expansion, wherein universes constantly arise from a larger expanding space. This speculation posits that our universe could be just one bubble among countless others, eternally expanding and collapsing. There are other fascinating thoughts as well, some suggesting our universe is a simulated world, built and sustained by advanced technological civilizations far beyond anything currently known to humanity. If this theory holds, our reality would be an illusion. But in the context of continued exploration, we must confront the idea that universal laws may not always operate as we have previously assumed. As scientists keep probing space, the complexities of our universe continue to grow, offering both clarity and new mysteries to solve. Ultimately, as astronomers like Carl Sagan so eloquently stated, somewhere something incredible is waiting to be known. Indeed, science's voyage continues with each new discovery, unfolding layers of wonder, complexity, and clarity that help deepen our understanding of the cosmos. As our understanding of the cosmos evolves, the role of technology and collaboration becomes increasingly critical. Instruments like the James Webb Space Telescope, JWST, are designed not only to capture images but to redefine our understanding of the very fabric of the universe. The immense data gathered by such observatories continues to expand our knowledge of space and time, allowing us to test long-held hypotheses and reconsider fundamental assumptions. For instance, JWST's unprecedented infrared sensitivity offers us a glimpse into the earliest moments of the universe, potentially shedding light on phenomena like the formation of the first stars and galaxies. In addition to this, the telescope's ability to observe exoplanets in greater detail than ever before might eventually lead to groundbreaking discoveries regarding the conditions required for life elsewhere. This shift in observational capacity can influence future theories in astrobiology, the study of life beyond Earth. Understanding the atmospheric composition of exoplanets may help us identify those with the potential to host life, guiding future missions to search for biosignatures, indicators of life in distant worlds. Moreover, the expanding field of gravitational wave astronomy provides another valuable layer of data, adding to our understanding of cosmic events. Gravitational waves, ripples in spacetime caused by accelerating massive objects like merging black holes, are often linked to some of the most energetic and extreme events in the universe. The detection of these waves is helping to reveal hidden aspects of the cosmos, such as the inner workings of supernovae, the dynamics of black holes, and the nature of neutron stars. Gravitational wave observatories like LIGO and Virgo are opening an entirely new window into the universe, complementing traditional electromagnetic observations, such as those made with optical and radio telescopes. In tandem with these developments, quantum mechanics continues to present an evolving challenge for cosmologists. At the smallest scales, the universe behaves in ways that seem counterintuitive to our everyday experiences. Quantum phenomena such as entanglement and superposition have profound implications for understanding the nature of space and time. The ongoing search for a theory of quantum gravity aims to reconcile the principles of quantum mechanics with the theory of general relativity, which governs the behavior of large-scale cosmic structures. One promising avenue is the study of string theory, which suggests that the fundamental particles we observe might not be point-like objects, but rather tiny, vibrating strings. If string theory proves to be correct, it could provide a unified framework for understanding all of the forces of nature, including gravity, within a single, elegant theory. The concept of dark matter and dark energy is another major frontier of modern cosmology. These mysterious substances account for around 95% of the universe's total mass energy content, yet they remain largely undetectable through direct observation. Dark matter, which interacts with regular matter through gravity but not electromagnetic forces, has been hypothesized to exist because of its gravitational effects on visible matter. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe, but its exact nature remains elusive. Together, these enigmatic components challenge our understanding of both the observable universe and the fundamental laws of physics. As we probe deeper into these cosmic mysteries, it's worth considering the philosophical implications of our discoveries. The more we learn about the vastness of the universe, the more we are confronted with questions about our place within it. What is the nature of consciousness, and does it exist elsewhere in the cosmos? What would it mean for humanity to make contact with intelligent extraterrestrial civilizations, should they exist? These existential questions are not only scientific in nature, but are also woven into the fabric of human thought, influencing culture, art, and philosophy throughout history. As we continue to push the boundaries of knowledge, these profound questions will undoubtedly persist, serving as a reminder that science is as much about exploring the unknown as it is about asking fundamental questions that shape our understanding of existence itself. Ultimately, the future of cosmology is bright, filled with opportunities for groundbreaking discoveries. Whether exploring the inner workings of black holes, investigating the mysteries of dark matter, or deciphering the early universe, the journey ahead promises to challenge our understanding of reality. Yet, despite our progress, there is still so much we don't know. For every question answered, a new one emerges, revealing the vastness of the unknown. This is what drives scientific inquiry, an insatiable curiosity to learn, explore, and understand the world around us. As we continue to venture into the cosmos, guided by the advances in technology and the spirit of discovery, we remain reminded of the words of Carl Sagan: "The cosmos is within us. We are made of star stuff. We are part of this grand adventure, an ongoing story of exploration and enlightenment that will continue for generations to come."